In this example, we have a simple torsional bar that is shown in this figure. So the shear stress in the aluminum shaft is not to exceed 120 MPa, and the vertical deflection of joint D is not to exceed delta equals 15 millimeter when a load of 30 kilonewton is applied. Neglect bending and assume that a bearing at C allows the shaft to rotate freely, no friction. So determine the minimum diameter required for this shaft. Okay, this is a design problem, right? This is a design problem to select the diameter, determine the diameter of the shaft to carry the load and to avoid the too large deflection of point D, right? So we have two criteria to meet. That is, the first one, the stress cannot be over this allowable stress, and the second one is that the deflection cannot be larger than this limit. Okay, so we're determining the minimum diameter. But we have to fulfill two requirements, right? Not only one, right? So the first one is that the tau max equals what? How to calculate the tau? That is Tc over J, right? And the second requirement is the phi, right? It's the delta, but we need to calculate the delta from the phi, from the angle of a twist. So you will see it later, like how we can connect them together. Okay, this phi equals TL over Gj. Right, in both of these equations, the J can be tied to D, right? This pi over 32 D to the fourth. Okay, so if we can connect this D here to these two requirements, then we can design this D. Right, so this is how we can solve this problem. So above all, let's determine those constants first. Okay, so in this example, we need to use the T, right? We need to use the T to calculate both shear stress and deformation. So what is the torque T? So when the P is added, P is here, that is 30 kilonewton, and it has an arm that is C, right? This is the arm. It will generate a torque here at point B. Right, this is the TB, right? So TB, the T or TB equals P times C, right? 30 kilonewton times 125 millimeter. That is 3,750,000 Newton millimeter, right? We don't want key n, we just need n, right? That's a Newton millimeter. Then the allowable stress, that is 120 MPa, and delta D is 15 millimeter. Okay, so based on this, let's see the first criteria. The first criterion, that is the tau max, right? This is tau max equals Tc over J. That is T, and this, what is the C? The maximum distance from the point, any point of concern to the centroid. That is half D, right? Half D over pi over 32 D to the fourth. And this will be 16T over pi D cube. Right, so this D cube equals 16T over pi tau max. Right, this will be 16 times 3,750,000 over pi times 120, and here is Newton millimeter, and here the unit of 120 is Newton per square millimeter. Right, this is MPa. So here you will have right. So yeah, but from here you can determine that d equals 54 times 2 millimeter, right? So you can do this calculation here, right? I will push you to do more calculations by yourself, since through the first example I have seen that many mistakes are just from the calculations, not the concept. Okay, d equals what? And its unit should be mm cube. Right? So here, just based on the first criterion, the diameter has to be not smaller than 54 times 0.2 millimeter. Okay, we have the second criterion. The second criterion is that the delta D equals 15 millimeter. So what is this? Right. Smaller than, not exceed, no larger than 15 millimeter. So this is actually, when we add the P, so this BD will be rotated about point B and rotated downward, right? So you get a triangle as shown here. So the delta D is just here. Okay, the delta D belongs to such a triangle. And here we have an angle. This little angle is just the phi, right? The phi B. Okay, so we have learned how to calculate this phi B. Right? This angle is just the same as the angle of a twist of this shaft at point B, right? So this is the phi B, and we can tie the phi B to this delta D. So you can see here in this triangle, the length of this side is just C, and this is delta D, right? So tangent phi B equals delta D over C, right? That is 15 over 125. Okay, so this is not a small enough number. Okay, this is larger than 0.1, not small enough. So you have to calculate the inverse tangent. So this equals what? And then the delta B can be calculated as 0.119 radian. So since point A here is fixed, right? So this phi B equals phi AB. Okay, this will be the torque times LAB over GJ. Okay, so we have to use this length, this LAB or A. LAB just equals A, right? That is 1,200. Okay, that is from A to B, not the whole length, right? Not the whole length from A to C, right? To be clear about this, then here will be 3,750,000 times 1,200 over the G. G is 27 GPa, so we need MPa, right? It's times 1,000. Then times the J, pi over 32 d to the fourth. Okay, this have to be smaller than 0.119 radian. Okay, so just from the 3 steps above, we have converted this criterion to the deflection criterion to a angle of twist criterion. Then we use this to do this calculation. Okay, so based on this, we can solve the D. Okay, you do this calculation by yourself. Okay, then this D had to be D just equals 61.4 millimeter. So our report is that D has to be no smaller than 61.4 mm. Okay, so from this two criteria, we got 2 results. From the first one, we got D has to be larger than 54.2, and from the second criterion, it's larger than 61.4. So which one we will take as the final result? So we will need to use the larger one, right? So the maximum value of 54.2 and 61.4, that is 61.4 millimeter. So the design report should say that to make sure this thing is safe and meeting all of these both of these 2 criteria, you have to make sure that the diameter of the shaft is not smaller than 61.4 millimeter. Okay, so this is a professional engineer's report, designer report. Okay, here we're done with this example, but I have two more questions, and this will be your in-class assessment. Okay, the first one is what is the torque in BC, the internal torque in BC? Okay. Internal torque in section BC. Second one will be what is the phi C? Okay, the angle of twist at point C. Okay, these are the 2 questions for you for the in-class assessment.